Okay, so good morning, everybody. My name is Michael Weigend, or Michael Weigend. I am a computer scientist and teacher, or I better should say I was a teacher. I'm retired now, but I still give some lectures on computer programming at the University of Münster. And that's why you see this beautiful building, this palace in the city of Münster, which is the main administrative building of the University of Münster. And okay, so I will give you many examples how to use Scratch in science classes, from simple storytelling, visualizing chemical reactions, and to discovering mathematical models with Scratch programs. I should say I was a computer science and chemistry and education teacher. So many examples are from chemistry. Please forgive me for that. By any chance, are there any people in the audience with a chemistry background? Can you raise your hand? Oh. I don't see any hands. Okay. So good to know. So let me start with what kind of digital tools are used for modeling and simulation in science education. There are a lot, and something really advanced are virtual laboratories. You can conduct experiments in a virtual environment, and you can do experiments which are too expensive and too dangerous to do them in real classrooms. The problem with these things is that you can't look inside the computer program. These are closed models of things taking place. And on the other hand, we have specialized modeling systems. For example, InsightMaker, it's a system for modeling system dynamics. Here, for example, we have this predator-prey model, and you have stocks and flows, and you can look inside the model and define everything. You can see simulation results when you do a simulation. So you can look inside the model, but this is really special. You need some time to understand it, to learn the technical aspect of this system and to be able to use it. And when you do this as a student, you do it maybe once or twice in your school career. So this is a huge disadvantage. There's a lot of technical overload. And we have Scratch and other programming languages, but Scratch is a multi-purpose programming language. And when you are able to program in Scratch, you can do many things, create many models, not only in science, also in arts. But of course, I focus on science projects with Scratch. And it's open and universal, that's the advantage. And I show some examples, and all the chemistry examples you can find in this studio. You're probably, I think, most of you are familiar with Scratch, and you know that there exists the Scratch website with millions of projects and organized in studios, and there's one studio with some chemistry examples. So I start with storytelling, visualizing the invisible. This is a gas chromatograph, a big machine which is used to separate substances, to separate and identify substances. Some schools have these machines, but this is really important topic in chemical education at schools. But it's closed. You can't look inside, but you can illustrate the principle, how this works, with a Scratch animation. So this is how it looks like. You have just two molecules traveling through some material, and when they reach the sensor line at the end, there's a signal which you can see, and that's the way how scientists identify substances in a mixture. So a very, very simple Scratch program, which looks like this. You have just 4 sprites and very, very small scripts for the sprites. This is a sprite. This is a script for one molecule, and it's a very simple program saying that this molecule glides from the starting position to the end position. So very simple modeling, but the program illustrates how this works. The molecules travel with different speeds. One is slow, one is fast. And you know, the effect is illustrated, but it's not explained actually. You still don't know why is one molecule slower than the others. So I will come to that, back to that later. Well, storytelling, you can dramatize chemical reactions. You can show them as theater plays. And here's an example from well, advanced chemistry class at high school level. 2 molecules coming together and forming a bigger molecule. And you can make these molecules talk. So this is an animation students can develop and explaining the mechanics of a chemical reaction. And in this, you have noticed that there's a lot of abstraction in this model. And abstraction is something which has some tradition in chemistry. All these chemical formulas, you know, from school, they are abstractions of real molecules. And you use different levels of abstraction. You can use these formulas, I think they're called molecular formulas, when you want to calculate how much alcohol you need for reacting with an acid to form an ester. This is the ester equilibrium. And in other cases, you want to explain how the mechanics of the chemical reaction works, and then you need a different type of formulas. And when you use Scratch, of course, you have the freedom to use all kinds of abstractions. You can use colors and simple shapes, which represent parts of molecules. This is an example which was created by a high school student. I did some programming in chemistry classes at high school level, and the reaction is called electrophilic addition of bromium to ethene. No, it's not bromium, it's bromine, the English word, sorry. And what you see is you have some brown, you have a brown fluid because of the bromine is brown. And when it reacts with ethene, for example, it gets colorless. And from these molecules, you get some kind of these molecules. Well, this is still simpler than the original molecule because some atoms are, you cannot see some atoms which are not important for the reaction. Well, a chemistry teacher would say, well, this is a wrong model. There are some errors. For example, atoms don't have color. But these students try to visualize or tries to make a connection between the molecules, which are invisible, and the visible effects. And I think this is a nice design idea that now there's no color in the molecules. But still, it's disputable. And I think this is a nice thing. When you create a model, it always has some errors. It's not perfect. No model is perfect. Each model is a simplification. And these student-made models are really a good start for discussions about modeling. And questions could be, does this model help understanding? Are there contradictions to theory? And when doing these discussions, you learn a lot. You know, you can publish your models in a studio, but I must say that many students actually don't like to publish, don't like to share their models, because they are afraid they are not perfect enough. They look, maybe they think they look a little bit childish or not professional. And many students really don't like to share their models. Okay, this was simple storytelling. Now it gets a little bit more complex. Real simulations with some kind of agent-based modeling you can do with Sratch. And you can explain things that are observable, and you can explain it with real molecule models. For example, you know, maybe you know that cotton consisting of cellulose absorbs water from the air, and it gets kind of damp when the air is humid. And you can explain the absorption of water with a model. And these are water molecules in the air, and they kind of stick at these oxygen-hydrogen groups here. And that's a phenomenon. Well, there's a kind of a bonding between the hydrogens of the water molecules. These are hydrogen atoms. There's a kind of bonding between these atoms and the red oxygen atoms. This is called H bonding. And this is modeled in a very simple Sratch model. You just have one type of sprite and many clones of this sprite. And this script describes the behavior of the molecule. And when the red oxygen part of the water molecule hits something white, so the hydrogen atom of this group at the cellulose molecule, then it waits just half a second. So it gets stuck in a way. So you model the effects of the hydrogen bonds, and you can see that really in your model, the cellulose, some water from the air sticks at the cellulose in your model. So this is explaining by a simulation. And back to the gas chromatograph. In the first animation I showed you, which was simple storytelling, just the effect was demonstrated. And now the effect is explained. Well, the effect is called retention. Different molecules have a different tendency to get stuck into the stationary phase of the chromatograph. And this getting stuck is modeled in this Sratch animation. And when it starts, this time you have 3 molecules, and the effect is different. So the bigger gets stuck more often than the smaller. And that leads to the separation of substances. So this is more than just a demonstration of the effect. This is really somewhat deeper explaining of the principle which is behind the gas chromatograph. Now in the rest of my talk, I want to talk about mathematical models and Sratch programming. You know, most of the scientific knowledge you learn at school is learned in the form of mathematical models. You have to learn some equations and have to try to apply these equations when you solve problems. And I want to show some examples how to make a connection between these mathematical models and Sratch models. And first about applying mathematical models. This is a German chemistry book, and you see there are many, many problems, many tasks where you have to calculate something. the term berechne appears at many places. And I just pick one task. And well, you have to calculate the pH of a solution and what happens when you solve this task. Well, you write down some knowledge, you know, how is definitions of pH and pOH. Then you know sodium hydroxide, it dissolves when you put it in water. Natrium ions and hydroxide ions appear, and the concentration of the hydroxide ions is almost the concentration of the sodium hydroxide you put into the water. You write down all this stuff, these equations. You do some algebraic reconstruction, and then at the end you have a result. And you write down a nice sentence. The pH of an aqueous solution of sodium hydroxide with concentration 1 mole per liter is pH equals 14. That's what expected to do when you do a test. And you do some simplification, and you use correct wording, and so on. The pedagogical intentions of these tasks is you connect theory to real world, and you elaborate and understand the mathematical model by just using it in solving problems, many problems. And when you have solved many problems, you get an idea how the whole thing works. And by the way, you practice basic knowledge, which you use in other areas too. You use definitions, units, which are used in other domains too. These are the intentions. And the problems are, for each task, there's only one solution. There's no challenge to creativity. It's always the teacher's perspective. The teacher picks the problems, and because he or she thinks it's interesting. And when the student has done such a solution, written down the solution, he or she shows it to the teacher, and then it's worthless. You can throw it away. It was just some exercise, nothing more. And this can be nicer when you do programming problems with Sratch, for example. This would be an equivalent programming task. So write a Sratch program that asks for the concentration of sodium hydroxide in water and then calculates the pH of the solution. And it could look like this with Sratch. Some kind of dialogue. Somebody asks you, hey, I can calculate the pH and what is the concentration of your solution? And then you can type in the concentration, and then you get the result. And you can design this in many ways, of course, and you can also program it in many ways. This is a very simple program because it doesn't contain any control structures. It's just a linear program. When you click on the sprite, then this happens and the dialogue starts. You can do it a little bit more complex and using an if-else block, because the simple solution only works when the sodium hydroxide concentration is rather high. When it's lower than 10 to -7 mole per liters, then you have to do something different. So what do you do when you...
sorry to interrupt you, Michael. Can you come maybe to the end? We have time for discussion.
Okay. How many more minutes?
I can give you 2 more minutes if that's okay.
2 more minutes, okay.
Yes.
So you can reflect the limits of the mathematics, you do all the stuff you do when you solve a traditional task from a textbook. Okay, so just quickly through the other examples, you can check mathematical models. The examples are a little bit more complex. I just show a few. For example, acceleration can be this equation you might know from your physics experience at school can be derived from this equation, but you never do it at school. At school, you just check if it's correct. You have the theory and you check if the experiments fits to the theory. And you can do the same with Scratch projects, just programming a simulation. And then you can do all the calculation with Scratch. And you see here this formula, and you can check whether this formula fits to what happens when you start your program. And you can see that these two numbers are almost the same. So this is kind of proof that the theory is correct in the simulation. So I think I switch all the rest and come to the conclusion. So many more models, but no time to show it. Okay. Okay, this is my conclusion. I think there's a lot of potential of Scratch programming in science education. You have individualized learning with open design tasks. And interesting is that students can express different interpretational theory, including misconceptions, which can be identified by the teacher. And I think all misconceptions are not to be considered something bad, it's something fruitful for learning and understanding. And they can initiate discussion, but the problem is not everybody likes sharing. But the requiring is that you need time for programming. You need additional time. Chemistry or science teachers don't like to give more time. But if the school curriculum requires programming, then part of the programming could be done in science lessons. And you need professional support. You need trained teachers who might help students when they find problems in their programs. So thank you very much for your attention and for the additional minutes.
So thank you very much for the presentation and the brilliant examples. Maybe you can close your presentation so that we see you for the discussion. So we have 5 minutes left. So are there any questions from the audience?
How can I close this?
I think it says stop at the top of.
I don't see any stop.
I think Steffi, you can also close.
Please do that, Steffi. I see stoppen. Okay, yeah.
Great. Okay. So, are there any questions? So, of course, I have a question. So, unfortunately, there were no chemistry teachers now here, but do you have the chance to try it out with teachers already, or what are your experiences?
Pardon? Again, I missed the question.
But do you have already experiences with trying it out with teachers as well? And what can you tell us?
Yes, I did some programming workshops with Scratch, also with Python, and also using Raspberry Pi and sensors. And these teachers many of these teachers have never programmed before, but they liked very much. Actually, these scientific projects were a reason for teachers to go into programming. And I also had the experience that students told me that they had never programmed before. But these modeling projects were for them a reason to start programming.
Oh, that sounds great. So let's see if we have some question from the audience.
Yes, I have one question. Are there any materials on your Scratch program for teachers? Do you provide some handouts or that can use?
Well, I think there exists some. Yeah, I don't remember where. There are some printed handouts for teachers in North Rhine-Westphalia, the federal state where I live, because these workshops were part of a program for teachers in North Rhine-Westphalia. Well, there is this studio. I think this presentation is recorded and you will find the studio easily. There are some examples for projects and you could look inside the projects and get inspired. I've written several books, and in 2 books there's also a Scratch section. These books are written for kids, but they contain chapters like Scratch in science. So they're about Scratch in general, but I think there's one chapter about Scratch in science.
Okay, thank you. I'm especially interested in this modeling, in models, how you represent it with Scratch. I think that's a really great thing to do. Thank you.
I think there are also a lot of examples in your presentation. So if we can upload also your presentation, so maybe it could help also, the other ones. And there we also have a comment, yes, from Simon Walters. I can really help with it can really help with learning. I use Scratch to animate moon phases with 10-year-olds. Yeah, I think there are a lot of possibilities. We used at least Scratch, at least pocket code in chemistry, also to teach the second law of Newton and to show also some formulas and that. So I think there are a lot of good ways to also engage in chemistry, and yes, with that. So Michael, thank you very much for your presentation again.